ladies and gentlemen, first of all, we would like to thank you for your coming in this guest lecture that is organized by Master and Doctoral Geological Engineering Program, Faculty of Earth Sciences and Technology, ITB, and also with the IAGI and Ikatan Pascasarjana Teknik Geologi ITB. And this guest lecture also supported by IAGI, Bidang Pendidikan dan Kursus, SM-IAGI ITB, Asproditegi, Dongeng Geologi. We really appreciate for your participation. Okay, we may know to start the guest lecture. The topic today session is large magnitude volcanic eruption. What impact would they have, and can we do anything about them? Let me introduce the invited speaker, Associate Professor Mike Cassidy from University of Brimingham. Ladies and gentlemen, there will be the short question and answer session at the end of the presentation. And to ask question, audience may use the chat box during the presentation or ask directly. Before we start the presentation from the invited speaker, I would like to welcome Dr. Mirzam Abdurrahman, the head of Master and Doctoral Geological Engineering Program, Faculty of Sciences, Technology, and also head of IAGI JBB, to give the opening speech to Pak Mirzam. Please, Pak.
Thank you, Dr. Idam. Thank you, Dr. Mike Cassidy. Good afternoon, everyone. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Yeah, as mentioned by Dr. Idam, that this afternoon we have special guest lecturer from my friend, my colleague from University of Birmingham. He is Dr. Mike Cassidy, associate professor, and if I'm not mistaken, he's also a research fellow from University of Cambridge and the University of Oxford, and also the co-founder of the Volcano 8. So today we would like to discuss about large magnitude volcanic eruption, what impact would they have, and what can do anything about them. I think this is very important for us who living in Indonesia as an active volcanic island. So thank you, Mike Cassidy, for your time, and also for your knowledge. I think not only to our student in ITB, but I also invite my student from the west to the east, and my colleague from PPMPG, maybe in other institution. Once again, thank you very much. Thank you, Dr. Idam.
Thank you very much, Dr. Mijam, for the warm greeting for the audience. And without further ado, please welcome Dr. or Associate Professor Mike Cassidy. The time is yours.
Thank you very much, Idam, and thank you very much, Mirzam, for the kind words. And salam alaikum, everyone. And it's great that everyone can make it. And wish I could be there in ITB with you in Bandung, but we'll do that another time. So today I'm going to be talking about large magnitude volcanic eruptions. And previously I've done talks on explosive or effusive eruptions, but this one is a bit more global, and it involves not just geology, but also kind of like global coordination, and also bits of philosophy and ethics, which I'll go into at the end. So it's going to be a kind of an all-round talk, quite broad, not just geological focus. And I hope you can stay with me and let me know if you have any questions about it. So this is large magnitude eruptions, and you know, in the last few years now, we've all lived through a very rare event, a so-called black swan event that was truly global in its impact, and that was the COVID pandemic, and it affected each and every one of us, whether that was indirectly through lockdowns or if we went through it ourselves. And as we went through this collective experience, different people took different things from it. Now, I'm not sure what lessons you learnt or the lessons that you took from it, from this sort of surreal experience, I guess. But for me as a volcanologist, it suddenly made my own research of studying large magnitude eruptions much more real and tangible. So I've been studying and researching large eruptions on volcanoes all around the world for about 17 years or so. But during the lockdown was the first time I had a distinct realization that these seemingly kind of rare events like COVID that happen every few hundred years which I naively expected wouldn't happen in our lifetime, were actually happening, and we were living through one. But the second lesson I learned was maybe even scarier than the first, I think. We knew that the biomedical community, reacted really well with amazing speed in developing vaccines, antivirals, and other scientific breakthroughs that really made a difference to the outcome of the pandemic and how long the pandemic was. But it made me think how volcanologists would fare in the next large eruption. And my assessment was quite poorly. And I think that's the challenge that I'll talk to you today about. So this basically comes off the back of a paper or comments that we wrote in Nature recently. And I'd encourage you to have a look at that. It's quite broad and simply written. And I think it has a lot of the main points that I'll talk about today. But today is my chance to go into these a bit more and discuss with you some of those important points and even have questions about it afterwards. But first of all, I want to bring you all on this journey. I know most of you, or many of you, will know about eruptions anyway, but I'm going to go through it gradually and talk about the Volcano Explosivity Index to start with, because I'm talking about large eruptions. But what do I mean by large volcanic eruptions? How large is large? Well, volcanic eruptions, as you know, are measured in a scale called the Volcano Explosivity Index, which goes from 1 to 8, 8 being a super eruption, which is the most explosive. And it's all got to do with how much ash is erupted out the volcano. And the scale is logarithmic. So that means each number is 10 times bigger than the last. So you might remember the Icelandic volcano, Eyjafjallajökull, which is in 2010. Now, you might not have made headlines in Indonesia, I'm not sure, but in Europe at least, this closed the airspace in Europe for several weeks and cost about 3 billion to the economy in 2010. So that was a VEI4 eruption, and because of where it was and the huge impact it had on commercial airlines, this had a huge impact in Northern Europe. Now, the famous eruption so I should say actually that last eruption, that was a photo I took of the VEI5 or the VEI4 eruption as it was going on, because I was there 2010 and took some measurements of that eruption. But this photo is not mine. This is a painting from the 79 AD Vesuvius eruption. Obviously a very famous eruption that buried the towns of Pompeii and Herculaneum in modern day Naples, and it killed thousands of people. And that was a VEI5 eruption. And so was the Mount St. Helens eruption in 1980 in USA. So if we go 10 times bigger now, we're going to move into areas that you'll be much more familiar with. So this is VEI6 eruption, the Krakatoa eruption of 1883. And of course, Mirzam Edan know this eruption, as many of you will have known and been there. And this was taken on a trip that I went with Mirzam and Idam to see the Krakatoa 1883 eruptions. So these are the deposits that we saw in Indonesia. I'm about 5 kilometers from what we think the vent was here. And the ash in this place, in this particular location, is about 40 meters high of ash and pumice. And there's a block here, which is the size of a bus, I guess, which was flung all that way, kind of 4 kilometers away from the vent itself. So that tells you about the power of these particular eruptions as they were going on. And of course, not just proximal to the volcanic eruption, but this eruption was heard 3,000 miles away in Australia. It created a shockwave that passed around the world several times, I think 11 times. And these hot ash-rich flows that traveled about the speed of a car or more, about 70 miles per hour, they moved 70 kilometers over the water to neighboring Java and Sumatra and burned people on the coasts of those islands, as we know, on the coast of those islands. And it killed people on the coast, as well as triggering large tsunamis that killed 36,000 people. So this was a huge tragedy, but the eruptions I'm going to be talking about today, these large eruptions, are 10 to 100 times bigger than this, namely VEI7 and VEI8 eruptions. So big, in fact, that their craters can be seen from space. And so much magma has been erupted from the crust that it collapses in on itself and forms a caldera. And they erupt so much ash that they could cover perhaps the UK in something like 40 centimeters of ash. So something like the island of Java, something like that, would be covered in about 40 centimeters of ash if it was equally distributed. So this eruption, despite being in Indonesia, and of course there was huge local effects in Indonesia, 100,000 people are thought to have died in Indonesia and the neighbor islands because of the pyroclastic flows and also a famine. But also back in where I live now in the UK, there was a 75% decline in UK's agriculture. And this meant that across Northern Europe, there was agricultural failures as well. There was global food price increased, and we had civil unrest in the UK, in Germany. There was famine in Europe, in the US as well, and in Asia, and it's associated with the spread of cholera outbreak in India, and it also altered elements of history. So I know this volcano, you think it's in the back door, in the back garden of Java. I know it's in Zimbabwe, but it's close to you here, but it's having these global impacts. So one of those impacts as well is that the creation of Frankenstein. So Mary Shelley, who wrote Frankenstein back a few years after the Tambora eruption in 1816, she wrote it in Switzerland along the shores of Lake Geneva, and there was particularly bad weather. There was very dark conditions because of the volcanic eruption, colder conditions, and also quite stormy eruptions and stormy conditions around Lake Geneva. And this created the spooky atmosphere that was associated with Frankenstein. And people thought that it was in this atmosphere that Mary Shelley wrote that book. And also, really interestingly, you might all familiar with the bicycle, but you might not be familiar with the fact that it really took off after the Tambora eruption. And this is because in Europe and the US, people started selling their horses and also started eating their horses because of the famine. And they sold the horses because they were poor, because they weren't able to feed themselves because of the agricultural decline. And so this really made the bicycle take off. And so these sort of two events, of course, it had a huge negative consequences for the world, but there's also these kind of funny incidences which had these kind of weird impacts that changed the course of history. So in VI8, of course, VI8 is a super eruption, and we haven't had one of these for 26,000 years. I'm showing Toba here, but the last super eruption was actually in New Zealand, in the Topor eruption, the eruption from the Topor volcanic zone. It's called the Oronui eruption. So the fact that it was 26,000 years ago, it means that it was much more or much earlier than human civilizations got going around 12,000 years ago. This means that we have no idea how modern civilization will react. So this image shows the fallout of ash from the Toba eruption, also from the Tambora eruption. It shows the line in this area in gray is the line that is covered in 5 centimeters of ash. So with Tambora and also the VI6 eruption of Pinatubo, mostly in the sea, and this 5 centimeter ash cloud is covering kind of neighboring islands over here, including much of Java for the Tambora eruption. But for the Toba eruption, which was a really big super eruption, you can see it covers an area that is now constitutes 3 billion people live in this area. So this sort of a super eruption would in fact cover the whole of the USA in about 10 centimeters of ash. That's how large these eruptions can be. But what would happen if a large eruption occurs today? So let's kind of take a better and a closer look at that. And we're going to look at the impacts from close to the volcano site, close to the eruption site, and then look at those impacts as we go further away and the global impacts. So within 100 kilometers of these large eruptions, would be finding dense hot ash flows, like these flows that you can see from Pinatubo, which were taken. Pyroclastic flows would destroy most buildings, power stations, oil pipelines, of course, infrastructure, and huge loss of life. And the ash from the pyroclastic flows, but also the fallout of ash directly from the plume, would bury towns and cities and sewage works, airports, in about 100 centimeters of fallout. And this loose ash would also mix with rainfall, and to generate mud flows called lahars. They can sweep away, of course, roads, cars, trains, power lines. And you know this in Indonesia all too well from the impacts we see from the Kelut eruption, from Serumu, and many other locations as well. But instead of just seeing this on a small scale like we've seen on Kelut, Serumu, etc., we'd be seeing this on a much larger scale, with a large magnitude eruption. And at this distance, we'd see mass infrastructure damage. We'd see lots of burial of infrastructure and buildings, and of course, a high fatality rate, probably up to about sort of 80–90% in this region, and a huge humanitarian crisis of wounded people who may have survived the initial eruption, but it would be hard for them to get out. So within 1,000 kilometers of an eruption would still be seeing up to 10 centimeters of ash. And that's enough ash essentially to collapse most roofs, especially if you add rainfall to that, which adds a lot of weight to the roofs. Many people might suffocate from inhaling the ash, or have serious breathing problems with ash inhalation as well. And also more ash means more damaging mud flows as well. And this could be over, instead of a kind of a regional area on the volcano, if you have ash in really far reaching regions, then this can really mix with the rainfall and cause these mud flows for weeks afterwards, perhaps even months afterwards. Of course, the pyroclastic flows and the landslides. I should say also, before I say that, ash can also hit transformers and electricity lines and cause them to flash over and cause them to fail. And we're seeing corrosion of power lines still after the Tonga eruption last year in 2022. So these are kind of long-term problems that could occur from these ash impacts, quite a distance from the volcano, 1,000 kilometers or so. And also we have pyroclastic flows and even landslides from these large eruptions, as we do see from the Tambora eruption, as we see from the Samalas eruption in Rinjani in 1257, as we see from Krakatoa. We see the appearance of tsunamis. And this is because you have a large collapse of the caldera, and this causes mass movement of rock and ash and displaces the water. And as we know from tsunamis, as we know from 2019 in Krakatoa, we know that tsunamis can have huge impacts to our coastlines. And these impacts could be far-reaching in the case of a large magnitude eruption. And these could also knock out seaports that are globally important for transporting trade, etc. They can affect fish stocks, destroy submarine cables, communication cables, and that's where we get most of our internet from. And we saw this with the Tonga eruption last year, that knocked out all the communication to that island because of these landslides underneath the ocean. And it could also block, as I said, marine trade. But the worst effects would be felt globally. So volcanoes contain a huge amount of sulfur, and an explosive eruption can transport this 20, perhaps even 60 kilometers up into the sky, up into the upper atmosphere, the stratosphere. So high, in fact, that it's above the weather and it can't be properly rained out. And what happens here is that the sulfur reacts in the stratosphere to form what's called an aerosol, a sulfate aerosol. And these act essentially as tiny mirrors to reflect the sun's radiation back into space and cool the earth. So I know what you might be thinking. You might be thinking, well, we're going through global warming, Mike. So maybe it's not such a bad thing that one of these large eruptions happening. But compared to the 0.2 degrees per decade of warming that's occurring from climate change each decade, so 0.2 degrees per decade increase on average, and which is really often, it's, as you can see right now, it's causing some really bad problems to the world in terms of extreme weather. What would be seen with a large magnitude volcanic eruption, similar to the magnitude that we saw in Tambora in 1815, is we'd see anything from a 1 to maybe a 3 or 4 degree drop in global temperatures within a year. So it's a really sudden, abrupt change, and it could last up to sort of 5 to 10 years as well. So this would significantly change, and this is a simple cartoon of what we're showing here. This could significantly change weather patterns across the world. We could be seeing Asian monsoons could disappear in Southeast India and also in China. We could be seeing widespread mega droughts across the world, especially in Northern Africa, which has borne the brunt of many large eruptions in the past in terms of their climatic impact. And we could be seeing huge changes in extreme weather too, such as summer frosts. So we saw kind of really cold spells in the summer in eastern US after the Tambora eruption, and these caused all the crops to fail in that eastern US region in the summer. So obviously this can have huge impacts, fundamental impacts to global water, because we'll be seeing droughts, and also food security, because if you start to reduce the radiation getting to Earth from the sun, then you also reduce plant photosynthesis, and that seriously affects global crop yields. So some estimates, and we want to kind of redo these estimates, but some estimates suggest that with a magnitude 7 eruption, it could reduce the population, reduce people's food, the amount of people, the amount of food that's there for people by about a billion people's worth of food. That could be removed from the system. It doesn't mean that a billion people will starve. We can make use with the food that we have already, but it means that the global food price will increase, and actually there will likely be some famines. And we're trying to apply for funds to quantify the food impacts and water impacts more properly. But essentially, the global distribution of temperature and radiation decrease won't be uniform across the world. It will be kind of concentrated in different areas. And actually, the global north, the northern hemisphere would be much more acutely affected compared to the southern hemisphere, and that's because there's more land masses. Islands and areas in the southern hemisphere would be less affected. And there'll be some areas which have much more colder impacts than others, and some will be relatively unharmed. But on average, we'll be seeing something like a degree or 2 or 3 degrees of cooling globally from this eruption. But since 1815, since the Tambora eruption, we're much more resilient as a global population. Volcanoes, for instance, are much better monitored. We have better healthcare across the world. We have better food yields and agricultural yields. We have greater technology, of course. And there have been success stories where, for volcanic eruptions, thousands of people have been evacuated before explosive eruptions. And a good example is Pinatubo in 1991, Merapi in 2010, and La Soufrière in the Caribbean, St. Vincent in 2021. And these saved tens of thousands of lives by these early warnings and evacuations. However, the world population is quite different from what it was in 1815. It's 8 times higher than it was. And the global trade that the world relies on has increased 1,000-fold since 1815. So we simply live in this different world. And of course, you know, human race has lived through many large volcanic eruptions, and I've mentioned some before, like the Tambora eruption, like the Toba eruption, like the the super eruption in New Zealand 26,000 years ago, the Oronuri eruption. So we don't think that these pose existential risks. We don't think that they'll cause humanity to go extinct. And that's a really important thing for us to mention. So we think by themselves, this won't happen. But an eruption in a modern, interconnected, globalized world brings these new vulnerabilities. And I'll go into that in a second in a bit more detail. But not to mention that we're also dealing with other disasters, not to mention, climate change that causes compounding risks such as extreme weather. We might have future pandemics to deal with as well at the same time. And of course, we're going through multiple global wars at the moment. All of this worsens any impact that a volcano can have by itself. So I think it's important to note that when we deal with these kind of a global risk from a large eruption, we don't think it will cause extinction by itself, but we're also dealing with lots of other global risks at the same time. So as well as affecting food and water supplies, as I talked about, eruptions can have cascading impacts on our modern critical systems. So what do I mean by that? Well, we can have energy impacts. Of course, if we see a loss of radiation from an ash cloud and sulfate aerosols, we'd also be seeing a loss from the energy that we can get from solar energy. We might be seeing blackouts from ash caused by damage to power lines. And we might be seeing that nuclear power stations might not be able to get their water cooled if there's, for instance, around the coast of the US or around the coast of Japan, they take a lot of their water from the sea, and these kind of these ash and pumice might be able to block these particular water in cool intakes. So that can have a huge impact on the amount of energy we can produce. Of course, if you also reduce the amount of water, then you reduce the amount of hydroelectricity and also biofuels. So it's a really kind of a multitude effect on energy. One thing that Indonesia has actually, which is great and is more resilient to this, is geothermal energy, which would be much more resilient to a shock like a volcanic eruption. We also would see huge impacts to transport and trade. We all know that volcanic eruptions can't fly through, or airplanes can't fly through volcanic eruptions. We saw that with Airflatlioko in 2010, but we also saw this in Indonesia in 1982 with the Gelunggung eruption as well, where the airplane lost all its 4 engines. But not only air travel, because if we have large pumice rafts in the ocean that caused by this large eruption, we've got so much ash in the eruption, then these can block our ships, and these can block our trade and our ports. And we've seen this in kind of small areas in Japan when they've had kind of submarine eruptions. And this would be really devastating for global trade, because global trade, 80% of global trade happens via the marine trade, via ships. And of course, with communication systems, and this is where our financial systems work through those communication systems. 99% of the internet traffic goes through those communication systems, but they run underneath areas which are very close to volcanic eruptions. And we saw this with the Tonga eruption, that all of the communication lines along the bottom of the ocean were broken by those submarine flows from pyroclastic flows, then moved submarine and severed all those. And it meant that during that Tonga eruption in 2022, the island went dark. We couldn't communicate with them. We didn't know what their situation was, how many people had died, and how they were faring. So if you think about that, but in a larger potential consequences and a larger humanitarian crisis, this could be a real problem. And of course, affecting things like our financial system, our economy, and that could have wide-ranging and global impacts. So this is a sort of a concept that I'm going to be talking about now, called global volcanic pinch points. And it was designed by my colleague and friend, Lara Mani, who I've been working on a lot on this topic of global volcanic risks. And she identified areas in which were close to volcanic regions, but also close to global infrastructure. So critical systems that I talked about just before, they cluster in certain places. And unfortunately, they also cluster near large volcanic regions. And we call these volcanic pinch points. And this is where a volcanic eruption would be especially consequential, even if it was smaller than a VEI-7 eruption. So if it's a small eruption, but it can have a large effect as well if they're in these particular pinch points. So here you can see the volcanoes in the world as red triangles. And we're going to superimpose air traffic density map. So you can see the density of air traffic. You see especially dense in Asia, around China, in Northern Europe and the US, near these large eruption volcanic sites. Also, marine trade is particularly dense around East Asia, Japan, China, and of course around Singapore, Indonesia as well. We can also see the submarine connectivity, submarine cables, particularly dense around the Mediterranean, and also again around Asia as well. And actually, I just want to pinpoint one place, which is the Straits of Malacca, which is just between, as you know, Sumatra and Malaysia. And this is where actually there's a very small point or small channel, which isn't very wide. And this could potentially be a choke point if this gets blocked. And I say this is globally important because 40% of all global trade passes through this point each year. 60% of the world's petroleum, so a lot of the world's energy. And this also sits next to, of course, as we know, Sumatra, which has about 68 volcanoes. So any particular kind of eruption that affects that channel, that could mean global consequences. Even if it's a small eruption, it can mean these really large ranging consequences. So our impacts on volcanic eruptions, as I've shown you in this talk so far, are very much dependent on the location of the eruption. For instance, an eruption perhaps in the middle of the US or in the middle of Russia might not have the impact that we're seeing with an eruption perhaps in East Asia and Japan, for instance. Also, the impacts depend on our preparations, how much we can prepare for a global impact, and also geopolitical reactions. So in an event of a large eruption, if we all globally cooperate, we can really minimize the effect and actually mitigate a lot of the harms that I've been talking about today. But if we have and we can smooth out the kind of global food system so that places that might be receiving a global shortage would receive enough food. But if there's a geopolitical overreaction, so if some areas like potentially Brazil, for instance, they start to ban exports on food or precious commodities, then this can have a global impact and it can cascade. So the impacts really depend on how well we cooperate as a world as well. And of course, the state of the world. You know, we have multiple wars going on at the moment in Russia and the Middle East at the moment. If we have a war between Taiwan and China, what will that mean in terms of kind of our response to a large eruption? So these are all factors that we have to take into consideration, and these really impact the effect that it has on our human society. So quick break from what I've just been talking about. I'm going to be talking about just common misconceptions, and I know many of you will know these already, so I don't have to go into this in great detail. But I sometimes give this talk to public, and this is some of the sort of misconceptions or falsehoods, I guess, that people have about volcanic eruptions that I'd like to cover. So, of course, volcanoes do get a lot of press, but there seems to be a lot of misconceptions, and that's why I want to clear up some of the ones that we see in the press, in the journalists. So one of the first ones is that all the volcanoes capable of large eruptions have been identified, and that's simply not the case. We know that there's been these eruptions in the ice core records and the tree ring records in the 6th century, for instance, that caused a mini ice age, or caused the late antique ice age. we don't know which volcanoes are responsible for that particular cool period. That most volcanoes are monitored, well, we know, especially in Indonesia as well, that only 30% of all global volcanoes are actually monitored. That we can predict a large eruption years in advance. I think this is simply not the case. We have no record. We haven't monitored a volcano before it's erupted in this large area. So actually the records that we have from places like Tambora in Indonesia, those historical records, are actually really important. And before the Tambora eruption, we know there was a few years of quite large earthquakes from those historical records. And so those are really interesting to kind of note. But otherwise, we don't really know what a large eruption looks like in advance and how quickly it could ramp up. That large eruptions, that volcanic winter could counteract climate change. Well, we've already talked about that. That it's not the case. What happens is it's too fast and it's too severe. So up to a degree of or 3 degrees of cooling, as opposed to the climate change that we're seeing, which is 0.2 degrees increase per decade. And you can see, even with that more gradual increase in temperatures through climate change, we can see it's having global impacts. And the last misconception I want to talk about is that large eruptions are super rare. So let me go into this now. So we can talk about how large eruptions occur, and we can try and find out this by looking at the rock record. And this is a really important area of research, to go out into places like Indonesia, to go to places, for instance, like the Tenega caldera in Bromo, to look at how many large eruptions it's had in its history, or Ruang, or even the large eruptions in Tambora beforehand, or Rinjani. And these are really important studies because they tell us how likely it is for that volcano to produce a large eruption. How often does that occur? So we can do this all around the world, and this has been done, although there's lots of incomplete rock records around the world, especially in volcanic islands where we can't, a lot of the ash falls in the sea. So that's where we need lake core records, or even marine cores, which are really important. But we can also use ice cores, and these are sampled from Greenland and Antarctica. And these preserve the spikes of sulfur that we see from large stratospheric volcanic eruptions. And we can date these spikes of sulfur that's erupted in these large eruptions, and we can tell how frequent they've been. So because we have these multiple ice cores from the North and South Pole, and we can correlate them between, we can date them, we can count how many there have been in a particular period, this gives us an idea of how many VEI7 eruptions equivalent there have been per century. So for VEI7 eruptions around the world, this is a global probability. Per 100 years, it's 1 in 7 per century. And for VEI8 eruption, a super eruption, something like what we saw in New Zealand 26,000 years ago, or in Toba, it's something like 1 in 170 per century probability. So an eruption occurring in the next 100 years, the combined probability is 1 in 6 per century. So in the next 100 years of my children, your children, their lifetime is a roll of the dice whether one of these large eruptions occur. And so I think this is a really important thing for people to understand, that this isn't really, they are rare, but they're not super rare. And the chance of these occurring within our lifetimes, within our child's lifetime, is about 1 in 6 per century. Now, due to the frequency of these events, it tells us that it will not lead to human extinction. But what it doesn't tell us is how modern civilizations will react to these large eruptions. So in the last 100 years, the world has changed in a huge way, as I've just shown. We don't know how a large eruption will be impacted by that. Now, if I was to tell you that there was a 1 in 6 chance of your house would fall down sometime in your life, I think you'd want to do something about it. And you'd want to maybe build reinforcements or call a builder at least. But what is society doing about this? Well, the short answer is extremely little. So unlike for climate change, unlike for pandemics or nuclear threats, or even planetary defense from asteroids, there's no coordinated international organization. There's no UN department responsible for helping to respond to eruptions. There's no global funds from governments to mitigate this extreme risk. In the UK, where I'm based, our environmental funding, only 1% goes to volcanoes compared to 50% that goes into climate change. And the same is true in the US for their funding of research science. So there's little research to quantify the impacts of food, water, energy, and financial impacts from a large eruption. And this is in stark contrast with planetary defense. So planetary defense, responsible for, and they've even got a logo down here, you can see, responsible for asteroid deflection or warning us about when the next asteroid will occur. This receives hundreds of millions of pounds each year. And volcanic risk is 100 times, hundreds of times, actually, it's actually 700 times larger than an asteroid impact for equivalent impacts. So an asteroid that would impact a kilometer-wide asteroid would probably have similar impacts as a large magnitude eruption, but actually a volcanic eruption is 700 times more likely to occur, this century at least. And NASA, the US Space Agency, even launched a mission last year which was impacted an asteroid to deflect its course. So it was testing out how we could deflect asteroids in the case if we had an asteroid coming our way, and it worked. And it was an amazing scientific accomplishment. And that ambition and investment, though, is just simply not there for volcanoes to do anything in this large scale way. That cost £300 million, that mission, and it was a theoretical a test of what we do in a large asteroid impact. We're not doing anything like that for volcanic eruptions. But what would it look like if the world took global catastrophic risks like volcanic risks as seriously as it does asteroids or pandemics or even climate change? So in the next few slides, I'm going to lay this vision out for you, and it's not sci-fi. It's all stuff that can be done technically right now. And in doing so, if we had a large eruption, we could save hundreds of millions of lives, if not more. So I'll explain this in about 3 slides. And the first topic is pinpointing the risk. So we could identify all the volcanoes that pose the greatest risk from large eruptions. This means doing those geological records, looking into marine sediment cores to really find out where the largest risk from volcanic eruption is. And this could be around Indonesia, it could be around the Mediterranean. We would have identified all the most vulnerable regions and the most globally critical regions, like what I showed before, probably around that East Asia, around China and Singapore area. That is certainly one of those, and there are more. We'd quantify the impacts on energy, on finance, on our global food and water security. And by doing all of this research, we could have a knowledge of which regions to focus our monitoring efforts, and which regions to focus on preparedness. So preparedness could mean shifting global resources like water or emergency electricity generators to that area before a large eruption. And we could also drive international policy change for greater resilience. So greater resilience if we have a global food shortage. We need to plan as a global community to make sure that this food and this water can be spread across different regions in the world so that no region goes hungry. So as I said before, only 27% of the eruptions since 1950 have been monitored with at least one instrument like a seismometer. And we can do a huge amount more in terms of this monitoring of volcanic eruptions and provided that key early warning. So even today, we can track the gas, the thermal signatures, and the ground movement of all on-land volcanoes from space every day. Now, we don't do this because there's simply not enough people or resources to do this. We could provide ground-based monitoring for the most dangerous volcanic regions. So that means increasing our seismic networks in particular. We could connect all volcano observatories in the world and to ensure continuity, to ensure that we can all be trained better, that we could share our data with each other. And this will mean that, especially with, as we see now with the growth of artificial intelligence on big data sets, this could improve the way we monitor volcanic eruptions. All of this means that we could provide early warning for all. It will allow for local and global preparedness. So that might mean evacuations of thousands of people. That could mean preparations of that global scale. As I said, maybe shifting global trade routes around to accommodate that. And the improvement of volcanic monitoring and an improved international response. So as soon as we're seeing that we're going to have a large magnitude volcanic eruption, then we might be able to speed up our international response and get those conversations going with international leaders really early. We can also ramp up preparedness. So this might mean something like nowcasting on phones. So for instance, if you have a large volcanic eruption, it's just gone off, you might have a message that might come through on your phone that says, clear volcanic ash off your roof to prevent collapse, because at this particular location, and it would have known your location from its cell tower pings, from which cell tower it's transmitted from. At this location, 50 centimeters of ash is expected in the next 2 hours. And a text like that, a notification like that, could save many, many lives in those areas. And this is saving lives not only from a large eruption, but also from smaller regional eruptions as well. So I think nowcasting could be a really good thing to happen. We can also have education and critical systems resilience in those most vulnerable regions. So we know that there's areas which have poor education that are really especially vulnerable, that have limited electricity or things like that, limited communication. We saw this in the St. Vincent eruption in the Caribbean in 2021. We had huge amounts of education and evacuation was really effective because of that education. They knew that a volcanic disaster or a volcanic eruption could mean a large disaster, so they evacuated really early, and 20,000 people evacuated very efficiently and were saved. If we could scale this up and do this in a larger way, then that would be fantastic. We could also have these global policy agreements in a disaster. So this might mean prioritizing fertilizers, prioritizing energy routes like petroleum that could be shipped to an area that we knew that was going to go through some trouble. Perhaps also shipping food or grain there when we know there's going to be humanitarian disaster or famines. This means also having policy agreements that agrees that there'll be no export bans, that we're not going to stop our trade because we're worried about our own particular resource. And it also means that we could do early agricultural action. So this means that if we know a large eruption's pumped in a lot of sulfur into the sky, we can project that maybe in 6 months to a year that Northern Europe might be going through some all the crops might fail essentially. So what we could do is we can plan early agricultural action. So we could say, okay, now we're going to grow potatoes instead of wheat, for instance, which is much more resilient to colder conditions and frost. So all of this means that we could avert humanitarian crises, which would be huge alleviation of global lives. And we could also mitigate global cascading problems. So I talked about cascading problems that affect that occur, and that could occur from famines, droughts, and also energy crises. So why aren't we doing any of this? I should say, you know, a large volcanic eruption could threaten the lives of billions, and the vision laid here would significantly mitigate this. So why aren't we doing this? Is the lack of awareness of the problem globally. We have poor funding and coordination of international bodies. There's simply nothing there in the middle. But we plan to change this. So research in this area, so trying to quantify the impacts on global food and water, energy and finance. With Lara, we're also soon to launch a non-profit organization and advocacy that is and risk mitigation. And this is called Volcano Aid. And this is also alongside Mirzam as well, which is great, and a global team of volcanologists. And it really plans to achieve some of the vision that I've laid out here already. So this is really where I want to move in the next few years and decades. And I think by doing this, we could achieve a huge amount and mitigate huge loss of life if there was a large eruption, that 1 in 6 chance. So I'm almost done, but I'm just going to spend a few more slides talking about what else could be done in the future. So of course, even with all those plans we've laid out already, we could suffer huge consequences just from that global climate change cooling, even despite making those preparations potentially. So another thing we could look into is research volcano geoengineering. So I know this sounds like a sort of a sci-fi topic. It's a controversial topic that geologists often dismiss and they sometimes ignore, sometimes seen as science fiction. But could it ever be safe or effective? And I think if it could be, then I think it would be great to know about this. And what are the ethical issues of doing volcano engineering? Well, this is something we've just published on, and you can go and read that. It's the ethics of volcano geoengineering. Is in Earth's Future journal. And this is with myself, Lara, who's also a volcanologist, volcanic risk, and also a philosopher, Anders Sandberg. So just to explain what this is, volcano geoengineering is the practice of altering the state of volcanic systems and altering volcanic eruptions to exploit them or mitigate their risk. And it's something that has come up in the past. In the World War II, the US and also the UK were considering bombing places like Japan and Japanese volcanoes to trigger large eruptions as a weapon, which is crazy to think about it now. There's even a conversation that was held in the UK Parliament from an MP, a member of Parliament, saying that why can't we bomb Mount Vesuvius in Italy to try and create a large eruption? So thankfully that didn't get done in the World War, but this is something that might get proposed in the future. And it's something that's been done in the past as well. So it's been purposeful and also inadvertent. So we'll know from in 1919, after the eruption of Kelut, which killed 5,000 people in Eastern Java, as you know, there was drilling of the crater walls, which actually drained the crater lake. And that alleviated the Lahar disaster in future eruptions. And of course, that needs to be continually drilled through. And actually, I'd be interested to know what the update is on that. Maybe people could update me afterwards about what that might mean. Actually, if it's still going on today. We saw in the USA throughout history bombing of lava flows to try and mitigate or try to deflect them from going in particular directions. We saw drilling of lake lava as well. In Indonesia and in Japan, we see debris flow dams that mitigate the impact from pyroclastic flows that dampen the kind of energy from those flows and make them less catastrophic. In Iceland in the 70s, we also cooled water with lava flows, with seawater. And also with degassed, gas-rich volcanic lakes, which actually prevented eruptions or gas-rich eruptions in Africa and Cameroon. And then most recently, in our search for geothermal energy, we've also drilled into magma chambers, and on at least 5 occasions in 3 different locations around the world. So in Hawaii, we drilled into magma by accident, nothing happened. In Kenya, they've also drilled into a magma chamber, and also most recently in Iceland, in Krafla, where they drilled into a magma chamber, and that's that figure in the middle. It caused a kind of small amount of smoking and ash and destroyed the well, and damaged the well drill bits. And so those are some images you can see there of volcano geoengineering in the past. So it demonstrates that we as humans are increasingly able to reach volcanic plumbing systems, but the ethical question is, should we? So it's a persistent, is it inevitable, I guess, is what I'm trying to say. Environmental intervention is common, and we see this despite the risks. We see this with asteroids, as I showed you before. We see cloud seeding, avalanches, forest fires, damming of rivers. So mitigation of other hazards seems to happen quite commonly. In the future, geothermal energy, obviously in Indonesia you have lots of geothermal energy, conventional geothermal energy plants. But as we also look to supercritical energy, and that means going much hotter temperatures, up to about 370 degrees, this generates 10 times the amount of electricity that conventional geothermal energy produces. But it's also associated with drilling into hotter rocks, potentially nearer to magma chambers. So this might happen more frequently as we try and transition into net zero and renewable energies. The economics of this, so there's huge demand for critical metals, things like lithium, copper, and actually it's been proposed that we can extract some of these from the hydrothermal systems around volcanic systems. And so this might get done, and this might make volcano geoengineering more likely. As we go through climate change, and particularly this decade, we're seeing much more increase in climate change effects. Policies in the future might make this more actionable. So there's been propositions or proposals to put sulfur into the sky to cool down the earth artificially, and in doing and also to bury carbon into the crust. These 2 particular actions that result from climate change might make volcano geoengineering much more realistic and feasible. And of course, we have that persistent volcanic risk. As I said, the large eruption is 1 in 6 per century. Authorities might act rapidly during an eruption or after, or before an eruption, and do something quite risky in terms of mitigating that particular volcanic eruption. So we support a proactive approach in terms of discussing things beforehand. So engineering, volcanic engineering could look like drilling into magma reservoirs, fracturing the rock for outgassing. It could mean water cooling the magmatic system below the volcano, and that could prevent an eruption, or it could at least prevent an explosive eruption. So outgassing of magma before could prevent an explosive eruption. We could also have post-eruption, so not just before an eruption occurs, but also after an eruption occurs. And this might mean the stratospheric aerosol of sulfur that I talked about in the first part of the talk, that could be coalesced and coagulated out of the atmosphere and removed, essentially rained out the atmosphere much quicker by perhaps using an aeroplane, a high altitude aeroplane, to inject something like water or something to make that sulfur aerosol fall out. So those are just 2 of the sort of like areas in which have been looked at. And I'd love to go into the philosophical approaches. I think I've run out of time a little bit at the moment, but you can ask me about that later. But essentially what I just want to finish with and talk about is that we provide guidance for volcano geoengineering. So what we say in this paper is that the uncertainty and the risk is basically too great for any short-term deployment of volcano geoengineering. But we currently have no idea whether the risks of attempting geoengineering outweigh the risk of not attempting it. So in the case of a large eruption. And research would really help us figure this out. So we do think that there's a strong moral case, ethical case, for us to do research into volcano engineering, but not necessarily do it in the short term. So I'm aware that a lot of this talk has come across as quite negative, but I want to send a kind of a positive note to finish with. So we come at a time where global volcano governance chats are starting to gain momentum. We've been having chats with IAGI, UN organizations like the UNDRR and the World Meteorological Organization, and we're continuing to have conversations with Volcano Aid on that. There's now much more attention and awareness and interest from international bodies like the Red Cross, humanitarian organizations, UN bodies, the World Bank, media, and different academic fields. And, you know, all of you are here listening to this talk as well, which is fantastic. And there's so few people working on this, and there's so little investment coming from global research or even global funding from governments, and also historically. What that means is that any small improvements we can make in terms of policy or disaster preparedness or research could have a significant impact. So we can, and we're making progress in mitigation, and I hope you will also join me in this kind of mission as well. So I'll leave it there, and thank you very much for your attention, and let me know if there's any questions.
Okay, thank you very much, Mike. Very interesting talk. Okay, now we are in the Q&A question and answer session. So if you have the question, you can use the chat or directly raise your hand, please.
Just a quick say hello to Malaweni. Hello, I saw your message. So we met in Switzerland recently last year, so that was great.
So please, okay, there is one person. I will read in the chat. This is from Winardo Kova. This is from I am Fania Malio and Geologi Engineering from Patimura. This is from Ambon, the eastern part of Indonesia.
Ambon, yeah.
And the question is about the volcanic rock in Ambon. My question might not be very related to today's topic, but this is still within the scope of volcano. The question is the stratigraphy of Ambon Island. There is an Ambon volcanic rock that consists of the andesite lava, basaltic lava, breccia, and the tuff. But the thing is, there is no volcano in Ambon. Maybe Mike, do you know about the Ambon, eastern part of?
I don't know so much about it. I can try to. I mean, I know you and Mirzam have been, so you might know. You might be able to answer this question better than I can. But you know, it's a very good point that in lots of places around the world, we do find these volcanic rocks. We do find tuffs and stuff like that. This could mean two things, I guess. It could mean that there is a volcanic eruption, or there was a volcano at some point throughout history, and we know that things, especially like lava rocks, they can last a long period of time. So it could be millions of years ago that there was volcanic eruptions. It's a volcanic arc, active arc. So what I think actually is more the case is that you've had sort of recent eruptions, perhaps not on the island itself, perhaps nearby, that have been transported there. But as I say, I don't know Ambon so much, so maybe Mirzam or Idam, you can help out with that.
Okay. Okay, Mike, thank you the answer. But okay, maybe we can next to the direct answer. There's some two persons already raise hand. First is Jananda. Jananda, please, you can open the mic directly.
Okay, thank you very much, Kang Idam. Hello, can everyone hear my voice?
Yes.
Yes, Jananda.
Okay, thank you very much, Mike, for the presentation. That's very insightful. And I have, well, at least two questions, but the first one is, how do the world researchers see the eruption from submarine volcano and their impact on the global volcanism. For example, like for transportation, because we know that the submarine volcano mostly located far away from the civilization and probably not directly impact, but some researchers put a lot of interest in that kind of matter. Can you please explain to me? I mean, like, give us some insight. Should we focus and then focus on that thing, or we put the priority on the aerial volcanoes first, for instance, something like that? Thanks a lot.
Yeah, thank you. That's a really great question, Janada. So, yeah, I didn't really talk about submarine volcanic eruptions too much. But you're right, they do get a lot of attention from volcanologists, at least. I think they can have quite big impacts, even though they can be sometimes far away from land. I should say also that there's volcanic submarine volcanoes that are really close to land and that could have really catastrophic problems. In Japan, there's lots of submarine volcanoes that are close to the coast as well. In Indonesia, I guess in northern Indonesia, we have some, especially also in the Mediterranean. So we have some large submarine volcanoes there. So I talked before about the Tonga eruption. That was a really case in point, a really good example. So that's an island that's basically the most remote island, almost the most remote place in the whole world. But yet this had a tsunami. It had a local tsunami, so quite high actually. And actually, luckily, luckily there wasn't too many people who died from that eruption. I think 4 or 5 people died from that eruption. But the nearest island from that was 70 kilometers away. And that had huge consequences. Not only did it have a tsunami to the neighboring islands, it also caused a tsunami from the shock wave. So the shock wave, similar to what we saw in Krakatoa in 1883, this also transported the world, or went around the world 7 times or so, and actually caused a tsunami in different seas, in the Caribbean, in the Atlantic. It also caused 2 people to die in Peru, on the other side of the Pacific, so thousands of kilometers away, damage to ports in Japan. So even an island like Tonga, and it also caused an oil spill in Peru that killed loads of birds and environmental life. So these are some of the cascading impacts it can have. It also, as I said before, it destroys the submarine cables around, and in terms of a global sense, that didn't impact the global world too much because it's so remote, and Tonga is not important on the global stage or in terms of connectivity. But if this happened in this happened in the US, or if it happened in the Mediterranean, or it happened around China and Japan, and Singapore and East Asia, then this could have huge consequences, even if it's a submarine eruption. So they're harder to monitor, submarine eruptions. I still think that the climate effects from a large submarine eruption would probably be less than a large subaerial on-land eruption. And that's because the water can strip out the sulfur a little bit, and that's what we saw with Tonga. Even though it was the size of a Pinatubo eruption, most of the ash, most of the sulfur went into the sea. And actually, it was only in the atmosphere, it was only 1/20th of the size of Pinatubo in terms of the sulfur output. So I think subaerial eruptions still deserve our priority, but some of those submarine eruptions, particularly in those areas which are really dense in global critical systems, deserve our attention too.
Okay, thank you, Mike.
Okay, thank you very much.
There is others question or additional?
Well, I have one more one more question. Is it okay,
Yes.
Kang Idam?
Yes, please.
Well, yeah, and in the case of submarine volcanoes eruptions, the main problem when we talk about generating the proper stratigraphy for that particular volcanoes are determining the age of the eruption itself, right? Do you have any a alternative for a getting the age, the exact age, because it's probably it's hard for us to do, carbon dating or something like that, or probably it's expensive if we want to do the potassium argon and something like that. Do you have any alternative for answering that kind of problem?
Yes.
Particularly
Yeah,
in studying the submarine volcanoes. Yeah.
yeah. So yeah, it can be tricky. The date, I don't do a lot of dating. I mean, so you could do, as you say, potassium argon or argon dating. Obviously, that's expensive, requires expertise and instrumentation. Another way is if it's within a marine sediment, if you have a core or even a shallow core, and it's in between marine sediment, then sometimes you can use microfossils in that marine sediment and use the kind of data in that way. So you could say, okay, that particular microfossil has appeared only in the last 1,000 years, and below that eruption, this microfossil is only appearing in this certain period of time. So yeah, so microfossil experts might be able, it's called biostratigraphy. They might be able to help you with that. If you're looking at really long records, then magneto stratigraphy, so with using the magnetic record, that can help. But that's really for kind of very long records. Yes, and you can do on those fossils, same fossils, you can do oxygen isotope stratigraphy. So if you dissolve those forams or little fossils, essentially, of biological material, and you measure their oxygen isotopes, then those can give you curves, and that'll enable you to date the volcanic eruptions.
Okay, thank you very much, Mike.
Okay. Okay, Mike. Now we are next question. So we have the Rikonita Hanif. Yeah, please. You can open the mic and also the video.
Okay, thank you for the opportunity. Sorry if my camera cannot open. My question may not be not related with the topic, but it's still within the scope of volcanology. As we know, Indonesia having a ring of fire, and then several volcanoes along the island of Java, Sumatra, Bali, and surrounding area have a crater or a caldera. However, there is something unique phenomena. That is a Toba volcano has a big caldera and very wide, filled with water, or we call a lake Toba. I want to ask why is it that Mount Tengger or Tengger volcano with Bromo complex volcano, which may have a big caldera too and maybe look like a Toba, but only contain a sea of sand, doesn't form a lake. What is the difference between Toba and Tengger volcano? Thank you.
So Tonga, do you say Toba, and the difference between which one?
Tengger volcano
Tengger.
and Toba volcano. What the difference
Is that
between that?
the volcano with Bromo in the middle? Ceremony, is that?
Yep.
No.
Yeah, please.
Yes. Okay.
Yes.
Yeah. No. That's an interesting question. It's something I've never really thought about too much. I think it's probably related to. It's probably related to the depth of the system, the caldera system. It could be that the age of the system might make an influence, and also the hydrological system. So Toba was, relatively recently, 74,000 years ago. It could be that through time, maybe in a few 100,000 years, Toba will start to fill up with sediment and it will dry out. But perhaps there's also Toba's situation. It's a very deep caldera, and the hydrological system is such that it fills it quite readily, whereas maybe in East Java, it's not as deep, and there's been some resurgence of the land from after the eruption. And there's also been some growth, I guess, with Seremu and Bromo and other volcanoes that have come up through the sort of caldera. So, and deposited lots of ash as well. So they could also block some of the hydrological access in terms of filling up that caldera. So yeah, it's not something I'm totally sure about, but those are some ideas, at least, yeah.
Okay, thank you, Mike.
Okay, thank you so much.
Okay, we have time. The others, the audience, if you have the other question, or maybe in this class. Barun, di sini, please. Or maybe you can use the video over there and this mic. Okay, tes. Okay. Tes. I want to ask you about again, sorry. Okay, Mike, I'm Bahrun, and I want to ask you about drilling project in several areas in the world. Firstly, it's quite something that maybe impossible to drill until the magma chamber because under the extreme condition. But I just knew about this fact that there are some drilling projects that have come to the magma chamber, and the question is what kind of drill bit that will resist in extreme condition with a high pressure and high temperature, like happen in Iceland or maybe USA. Thank you, Mike.
Yeah, good question. I don't really know the exact sort of drill bits and stuff like that they used. I know, so in Iceland, what happens, they drill down and then all of a sudden they hit this pocket of magma, not a big pocket of magma, but then they found all this glass that came up, and so the magma quenched really quickly. But the drill bit they lost the drill bit, it dissolved, or it was completely removed. So they don't have the expertise at the moment to kind of like drill through the magma persistently, but they've been able to reach the magma, so around the surrounding rocks, which will also be very hot, and actually, just kind of pinch the magma itself. But we also know from Japan as well that they've drilled into not magmas but fluids that are 500 degrees centigrade and above, and there's different challenges that come through this in the geothermal industry. Of course, we have scaling of the pipes, so silica, for instance, will and calcite, other minerals will start to crystallize on the pipes as we start to get fluids out, as because the steam condenses really quickly, it dissolves all that silica. And also, corrosion of the drill bits, because of not just the high temperatures, but also the fluids, hydrochloric acid, hydrofluoric acid, these are really damaging to metal. So I think these are technologies actually that are being increased all the time now, and because we see these, we see the technology wanting, or the communities to want to drill into these hotter areas. Like there's projects that are planned in the US, Iceland, New Zealand, Italy, Mexico maybe, that are planning to harvest this supercritical geothermal energy. And this means drilling at much higher temperatures and much higher pressures, etc. And so that technology to make those drill bits more resistant to fluids and high temperatures is going on right now. And I think in the next few years, it will improve a lot.
Okay, that's enough. Great answer. Thank you, Mark.
Okay, thank you, Bahrun. We still have time, maybe one more question from the class? Maybe from the audience in the chat box. Wait. Sudah? Semua? So please.
Mike, maybe I have short question related
Please,
to
Pak Bidang.
yeah, not directly related to what you're talking about. This is related to our student. Is there any possibility for our student to be involved in your research and possibility to study abroad in Birmingham University? Actually, they want to ask about the possibility, but I don't know. They didn't ask directly to you, Mike.
Yeah, no, that's good. So what we've found is with the UK government and the rules there, they make it very difficult, unfortunately, to come study. So even if myself and Seb and others, Sam, we want students to come, I have to admit, is difficult, unfortunately, which is something we're sad about. But there are possible ways to try and get a scholarship from Indonesia. The best way probably we've found in the last few years, so we've tried with multiple students, as you know, Mirzam. One of the best ways probably is to get a scholarship from Indonesia, from the National Scholarship Scheme, to come to do a master's or a PhD with us in Birmingham or in the UK, and we'd love to have you. So that's probably the best option. Undergraduate, I think, if you mean just also undergraduate, that is possible, but it's just expensive. International students in the UK universities have to pay about 20,000 UK pounds, which is a lot per year, to come to do an undergraduate degree. So as I say, the best way is to get a scholarship and then in Indonesia and then bring it to the UK. And as I say, we're very happy to have you.
Yeah, okay. Thank you, Mike.
Okay, thank you very much, Mike, for the information. Okay, maybe if there is no question, thank you very much, Dr. Mike, for your talk. Very interesting. And we have some from the committee have a certificate for you. Thank you very much for your time and
thank you.
Yeah, maybe Pak Bidang will explain something. Greeting.
Thank you.
Yeah, this is just something like appreciation for your talk this afternoon. More than welcome for your coming to ITB to pick up it directly, Mike. If I'm not mistaken, next year on January, Seb will come here with Sam.
Oh, I don't know.
Okay.
I think Sam is just going by. I think that's not linked, unfortunately. But
Okay.
Yeah. But I'd love to come again. Is Sam going in January? Is she?
Yeah.
Oh, nice. Okay. Yeah.
Okay, thank you very much, Mike. And then, ladies and gentlemen, we have finished the guest lecture of the day. We have learned a lot today regarding the large magnitude volcanic eruption and what impact would they have, and can we do anything about them. May what we have learned today will be useful for us in the future. And before we close this session, let me inform to you that the next week we will have another interesting guest lecture. So maybe we will inform you by WhatsApp or check the Instagram in our program study. Thank you very much for Associate Professor Mike Cassidy. And before we close, maybe we will have the photo session. Please open your video and Elin. The committee will please. We'll take the picture, please.
All right, for the first slide, please smile widely. Your best smiles. On 1, 2, and okay, we almost get there. Please open your video. Okay, and 2 and 3. Wait. Okay. On slide 2, okay, and 1 and 2 and 3. And last but not least, slide 3, and 1 and 2 and 3. Best smiles, everybody. Thank you so much for your cooperation.
Okay, thank you. Thank you, everyone. See you next week. Stay healthy and have a nice weekend. Assalamualaikum warahmatullahi wabarakatuh. Thank you, Mike. Thank you.